So welcome to lecture 3. And we had this very nice cartoon in the last class. So we had the mathematical body, which is just an abstract collection of particles. Okay? And the domain of this body is denoted by this symbol B, scripted B. Okay? And any particle here is denoted by scripted p, small p. And then we have what is called the current configuration. And this configuration occupies the region R in the three-dimensional space. And then we also talked of the reference configuration. Which occupies the region R ref, isn't it? So a particle has its location small x in the reference configuration. Okay? And the same particle has its location at small y in the current configuration. All right, so it's the same particle which are at x and y. In the two configurations. I'll just like to introduce a new notation here. See, in the textbook, whenever you have a scalar, they denote it by lowercase letter, let us say small a. But whenever you have vector, they denote it by bold letter, bold small letter. And whenever you have tensor, I think you have gotten exposed to tensors, second order tensor, for example, in the math class, that is denoted by bold capital letter. Okay, so this is all good when it is in the textbook, but when I'm writing it, no, I have to emphasize while making it bold. So what I'm going to do is, for scalars, I will use whatever is in the textbook, that is small letter but not a bold. For vectors, I'm going to put a tilde below. Okay, that would mean that it's a vector. And till now we have been doing what? We had this arrow on the top, no? But we are dropping that arrow symbol and we'll use a tilde below. And if it's a second order tensor, I'm going to use two tildes below. Okay? If it's a third order tensor, so this is for the 0th order tensor, there is no tilde. This is for the first order tensor, then for the second order tensor, and if it's a third order tensor, you can guess I will use three tildes. Okay, and likewise. So that way I don't have to make extra level of making it bold. And sometimes it may be ambiguous also. If I do not make it so bold, you might be confused whether it is scalar or vector. Okay, so please understand this notation, very simple, and this is what you have to follow for this class. Okay, I hope there is no question on this. Yeah. Okay, so with that thing in mind, then this y is a position vector, no? So it becomes with a single tilde. And this x is now also with a single tilde. And this map, which takes p to y, you remember, that's the map xi, isn't it? So that's a vector map, no? So xi with a tilde. And its argument is p. Whereas the inverse map, that's a scalar map, and it's Xi inverse, which takes y as the argument. Okay, so I think we are all familiar with this. Similarly, over here in the reference configuration, when it goes, the map is denoted by Xi, but we also used this subscript ref, right? And it again takes the particle p as its input or argument, whereas the inverse one that has Xi inverse ref, okay, which takes the position in the reference configuration as the input. And then we also saw that these two maps can be used to generate this map directly from reference to the current configuration, and which we denoted by y hat, okay, which takes the reference configuration as an input and gives current configuration as an output. Okay, and of course then you can also think of the inverse y hat inverse, right, which takes y as an input. Okay, so I hope this picture is clear to everyone. All right, so this is something that we had already done in the last class. Introduction of reference configuration, current configuration, and the mapping from reference to current. And this mapping is also called deformation map. Okay, whereas these Jis, these are configurations, right? Okay, then a very interesting concept that we are going to learn next is what is called description of physical quantities. See, these are very important topics to understand, because any book that you open or any paper that you open on solid mechanics or fluid mechanics, they will be using this language. And if you're not familiar, you won't be able to understand the basic things. Okay? And there are two ways to describe physical quantities. That is spatial, or what is called Eulerian, which people in fluid mechanics mostly use, which are the same thing, spatial / Eulerian, or referential / Lagrangian. The next one is used widely in solid mechanics. Okay, forms. So there are two ways in which we denote physical quantities. Let me just give you an example. So suppose I want to describe temperature in the body. Okay, temperature, which we denote by, let us say, theta, because that's what the textbook uses. So theta, and temperature is scalar quantity, so there is no tilde below. Okay, so this theta can be thought of as a function theta star. Okay, depending on the particle p. All right, So as you change the argument, you get temperature of different particle in the body. So theta star is the function. And you see, this is a way in which you are denoting temperature in terms of the particle. So this is also called material description, okay? It's called material description. You could, also write this as theta star, and then for particle P, you use this inverse map, chi inverse of y, isn't it? So this thing can be together thought of as some theta bar, which is a function of y. Okay, so you see, in this description, you are expressing temperature of the body in terms of current location of particles, in terms of current location. So this is called spatial or Eulerian description. Okay, so this is spatial slash Eulerian description. So whenever you are expressing physical quantities in terms of spatial or Eulerian description, sorry, in terms of the current position, that we call spatial or Eulerian description. Okay. The same thing you could also think of denoting this particle in terms of the position of the particle in the reference configuration, right? So in that case, you have this reference inverse map, and it takes then the position of the particle in the reference configuration as an input. So this can be thought of as a different function theta hat. Okay, depending on the location of the particle in the reference configuration, correct? And this is called referential slash Lagrangian description. So I hope this two new concept is clear. So whenever you are denoting expressing physical quantity in terms of the current location of the particle, that's Eulerian. If it is in terms of the referential location of the particle, that's Lagrangian. Let me see if you have some question here. Okay, there is no question as of now. At the same time, understand or be clear that this referential function, so this thing over here, this referential function, this does not mean that it is the temperature of the particle in the reference configuration. So I'll just write here. Many students or even researchers confuse it with thinking that this is the temperature of the particle in the reference configuration. This is not correct. You see, it's just a way to write down temperature. It is still the temperature of the particle in the current configuration. All right. So this is not correct. I'll put a cross sign here. So it is still the temperature of the particle in the current configuration. So this thing is correct. So whether it is theta bar or it is theta hat or it is theta star, they are all denoting the temperature of the particle in the current configuration. It is just three different ways to express temperature. The same quantity, that is temperature, in the current configuration, whether you want to express it in terms of the position of the particle in the current configuration or the position of the particle in the reference configuration or the particle itself. Okay. So again, it is the temperature of the particle here in the current configuration. It is not the temperature of the particle over here. It is over here. But just expressed in different ways. So somebody is asking how we are arriving at theta bar and theta hat functions. So that is, of course, a good question. But as of now, we are just saying, we are just introducing these functions. Of course, one person could, for example, measure. Let us say you have a body in the current configuration. A person could measure temperature at different points, and then he would get this Eulerian description, theta bar of y. So he will get that function directly, right? But then to get theta hat, which is a Lagrangian description, for that one has to know the relation between y and x. What was the referential position of the particle which is currently at y? So if one knows that, then one can also get theta hat, isn't it? So basically, theta hat of x can also be thought of as theta bar of this y hat of x, isn't it? So this is a way, if you know one, you can get the other one also. But for that, you have to know this deformation map. Y hat should be known in that case. So somebody is asking, theta star is a configuration? No, theta star is not a configuration. Configuration is only when it is giving you the location of the particle. Okay, so by configuration, we mean the position of the body, not temperature. Okay, so I hope I have cleared your doubts. We can now we can move further basically. So of course the next thing that comes to our mind is what is called Eulerian and Lagrangian spatial derivatives. So these are two separate things. So you see, we just now saw that theta is equal to theta hat of x, isn't it? Or we said theta bar of y. Now you might be interested in knowing how is theta varying in the body, right? So here is your body, that's the current configuration. So any particle is denoted by y here, current configuration. So you might want to know, for example, if you move in this direction, along E1, how is temperature changing? What is the rate of change of temperature with respect to the coordinate along E1? Right? So that means you want to know del theta over del y1, isn't it? If y you denote by yiei. Okay, you are all now for till I think you have gotten familiar with the Einstein summation convention, right? Whenever you have an index repeating, you have to sum over the index. So when you denote this position vector y as yiei, then yi's are the components of that vector with respect to the basis ei. Okay, so del theta by del y1, for example, is the derivative in the E1 direction. So this, if you want to know this, you will say it is del theta bar over del y1. But you may also want to know how is this temperature changing with respect to referential coordinate. You know, just for, I mean, you will see later on why, but let us say for now, say just for fun. So if I want to know del theta by del x1, see, they are not the same. It is not the same as del theta by del y1. They are not the same, right? Because x1 and y1 are two different coordinates. X1 is in the Lagrangian or in the reference, and y1 is in the current configuration. Just to tell you why it is really different, let me draw the body in the two configurations. So this is reference and this is current, or also called deformed configuration. So suppose here in the reference configuration, if you move along E1, just think of a line in the body, engraved line in the body at the point X, okay, and you're moving along E1. That same line, where, how will that look like in the current configuration? So in the current configuration, because of the deformation, that line may have become curved, right? First of all, it starts at y, not at x. It starts at y, and it may be moving like this. That could be the, you know, the what is called image of this line in the reference configuration. So when we find out del theta by del x1, that means we want to move along the horizontal line in the reference configuration and find out how temperature is varying. That is del theta by del x1. But that is same as when you move along this particular line, you see. In the deformed configuration, you then have to move along this curved line. It is not the same thing as moving along this horizontal line over here. Okay, so I'll just put it here that it is not the same, it is this one. This thing is actually del theta by del y1. Okay, whereas this thing over here, that's del theta by del x1. Somebody is asking, if the continuum is a fluid, that line may not even be continuous, right? So of course, if you have a fluid and you really stir it randomly, then that is true, it may not be a continuous. But as long as you don't do that, if you are not stirring it randomly, then that line can still be a continuous line. Okay, so I hope you are now clear about the two derivatives, the Lagrangian derivative and the Eulerian derivative. They are not the same. Okay, and of course there is a way to relate those two. There is a way to relate those two, and let me do that here. Um, Before doing that, I would also like to tell you something. See, when I say Lagrangian derivative, then you know that you have to take the derivative of theta hat with respect to x1. So this is Lagrangian, because theta hat is something which depends on x1, x2, x3. And when you want to take the Eulerian derivative, then you want to take the derivative of theta bar with respect to y1. Okay, so this is Eulerian. Often it is very cumbersome to keep using hats and bars often. But for clarity purpose, of course, one should use that. Otherwise, it is cumbersome, isn't it? You also take an extra effort in writing bar or hat. So in that case, people just say del theta by del y1. Okay, but then you have to understand that it implies del theta bar by del y1. Okay, similarly, one could just say del theta by del x1, but you have to understand that it implies del theta hat by del x1. Okay, now this is clear, because when you are taking the derivative in the denominator, you are writing whether it is x or y. But suppose you must have been introduced to the gradient function also. Gradient, divergence, curl, or gradient. So the gradient, one uses this inverted triangle, isn't it? And you see it's a vector of operation, because you have to take the derivative with respect to all the three coordinates, for example. So being vector, I could use a tilde below. Either you make it bold or you use a tilde below. Okay, so you can say gradient of theta. But you see, when you write like this, it is not clear whether it is with respect to Lagrangian, is it the Lagrangian gradient, or is it the spatial or the Eulerian gradient, isn't it? So therefore, often people will also use a subscript here, let us say y, to denote that it's actually the Eulerian gradient, or you just subscript here x to denote that it is actually the Lagrangian gradient. In the book, they say that one could also write this as, with a small g, grad theta, and this one with a big G, theta. So small g means it's the Eulerian, big G means it's the Lagrangian. Okay. So you likewise have divergence, small d or big D. Similarly, you can have curl, small c or big C. So all these are whether the derivatives are being taken with respect to Lagrangian or Eulerian coordinates. Okay. So I hope that so far it is clear. And as I told you, you can also relate the Lagrangian and the Eulerian gradients. let me show you, for example. So the Lagrangian gradient, for example, you will see it is del theta hat over del xi, isn't it? With respect to, let us say, ith coordinate. So this thing you can also write as, you see, theta hat is same as theta bar, no? If expressed at the corresponding positions. So we know that this is at x. So you can also write the same thing as del theta bar, but at y hat of x, isn't it? And now you take the derivative with respect to the Eulerian coordinate, which is, let's say, yj. Okay, and then of the Eulerian coordinate del yj hat with respect to the Lagrangian coordinate xi. So you see, whatever was supposed to be done here, it has come over here, and it's simple chain rule. Okay, so things are getting a bit difficult, but I'm going very slow. If you have any question, please feel free to ask me. And I think you all must have learned till now that you can't write it as del theta bar over del yi into del yi hat over del xi, because here you have I repeating thrice. I is appearing thrice, so it is not allowed. In summation convention, index can appear maximum twice only, right? If you have to sum it, it has to appear twice. It can't appear more than 2 times. Okay. Now, what is this thing over here? So you know that y is this function y hat of x. Okay. Or expressed in component wise, when you write it component wise, you can say that yj, the jth coordinate, is given by the jth coordinate of this function y hat in terms of the 3 components x1, x2, x3. The x still has to be all 3. Okay, and then you can think of del yj over del xi as this del yj hat over del xi. Okay, so you can see what is this thing over here. And this del yj over del xi has got a name also. This thing, this is also called fji, big F, the gi component of the deformation gradient matrix. Okay, and it turns out it's a second order tensor, this deformation gradient. We'll come to that more clearly later on. Okay, so one writes it as big F with 2 tildes below, because it's a second order. It has 2 index, no, so therefore it's a second order tensor. If it has just 1 index, it's a first order tensor. Sorry. It's a second order tensor. You guys are not asking any question. I hope things are clear for all of you. So with that, we can also write this as Fji del theta bar over del Yj, or we can write it as F transpose Ij, isn't it? Fij is same as F transpose Ij. Del theta bar over del Yj. And one can then see that this thing on the right hand side is actually simple matrix multiplication. How many of you are aware that this is a matrix multiplication? Let me create a pool here. So it is a multiplication of matrix with a vector. Okay, so I see that it is 50-50. So that is not a good sign. So you see, you have to really revise. It's more on the no side. More people don't know it that it's a matrix vector multiplication. So you have to revise my notes. I told you lectures 1 to 6. During this weekend, please revise it. Okay? I'm anyway going to come back to it later on, but for now, just to keep moving ahead, this is actually matrix multiplication, matrix times vector. So that means we can also write this as gradient of theta. See, on the left hand side, it's the gradient with respect to xi. So we can express del theta del x1, del theta del x2, del theta del x3, all three together as this vector gradient with respect to x. Okay, and that's equal to, seeing here, it is the deformation gradient tensor transpose multiplied by the gradient, the Eulerian gradient of temperature. Okay, so this is how you can relate Lagrangian and Eulerian gradients. Somebody is asking what is I and j. So you see, I and j is just denoting the component, right? So I goes from 1 to 3, j goes from 1 to 3. So I in this case could be 1, 2, 3, any three of them. It could be del theta by del x1, del theta by del x2, or del theta by del x3. I'm not writing all three separately. Just by writing del theta by del xi, I can convey to you that it can be any of the three. Okay? So that's the advantage of using indicial notation, that you don't have to explicitly write all the three explicitly on the paper. Just by writing del theta by del xi, I can convey to you that it could be any of the three, del theta by del x1, del theta by del x2, or del theta by del x3. how we calculate f? So you see, that is the definition for f here, over here. Fji is del yj hat by del xi. So to calculate f, you have to know this function y hat. The deformation you have to know. If you know the three components of that deformation function, y hat 1, y2 hat, and y3 hat, if you know those three functions, you simply take the derivative. And you can then get fji. Okay, we'll get to it more clearly later on. Yeah, y hat has to be known. Okay, so this is how you can relate what is called Lagrangian and spatial gradient. But for now, all that I wanted you to know is that there can be two kinds of spatial derivatives, Lagrangian and spatial derivatives. Okay, sorry, Lagrangian and Eulerian derivatives, and they are not the same. So I hope this thing is clear to every one of you. Okay, having seen this spatial derivative, of course the next thing that comes is time derivative. Because a body is actually evolving in time, so we have to be able to take time derivative also, isn't it? So that's the next thing, which I'll write as motion of a particle, or I should say motion of a body. Okay, so how can we mathematically describe motion of a body? So one of you had already said to me that the configuration map can also depend on time. So that's the way to mathematically describe motion of a body, isn't it? So you can say that the current coordinate y is a function of both the particle p and time t. Okay, where this particle p is any particle in this body b, and this time t could be, let us say, between t0 and t1, so during which you are looking at the body. Okay, so this is how you can mathematically describe motion. And what's the region occupied by the body? The region occupied by the body, this r, it's also then changing with time, no? So this is simply when you pass to the configuration, the entire body b, when you pass all the particles, then you get the region, right? So that's why I'm passing the body itself, and you get the entire region. Okay, so likewise you can also think of, this is the position of the particle, you can think of velocity as well as acceleration. So the velocity, if I denote by v, okay, maybe I should use scripted v. So this can be thought of as a star function, v star, depending on the particle and time, isn't it? And then it is, I hope it is clear to you that it is same as the partial derivative of this configuration x with respect to time. Right? And likewise you can think of acceleration a, which is this function a star of particle and time, and it is same as second derivative of this configuration map with respect to time. Okay, and having seen that you are writing velocity, so you see this is the material description, no? This is material description when you're writing it in terms of particle. But with those maps present, you can now express velocity in both Lagrangian and Eulerian forms. So the same velocity, this v star, you write as p in terms of the inverse map okay, of y comma t, and then you have a t, another t, isn't it? You see that the map is now dependent on time also, so therefore you have to have the time inside. T is appearing 2 times. I'll just show you again. This y is a function of p comma t, so therefore this particle p is then xi inverse of y comma t. So inverse function will be different at different time. At several other places you will also see this written as xi inverse with a subscript t of y, which implies that you are taking the inverse at a time t. I hope that this is clear to you. It is important to take the inverse at a time t because at 2 different times at the same location y, you may have 2 different particles. So what I mean to say is that if you just write it as xi inverse y, it is not correct, because at time t1 you have particle p1 at y, and at time t2 you have particle p2 at the same location y. So this inverse will give you 2 different p's. So therefore it is not defined, it is not well defined. Okay, so now with this thing you can then see that it is v bar of y comma t, right? Likewise you can think of also the Lagrangian description in which you will write this v star as an inverse of referential map x comma t, and then this induces a different function hat of x comma t. So these are, so this then becomes the Eulerian description of velocity in terms of current position of the particle, and this becomes the Lagrangian description of velocity in terms of referential coordinate or referential position of the particle. And again understand that the velocities, when you write this Lagrangian description, it does not mean that it is a velocity of the particle in the reference configuration. It is not that. It is the velocity of the particle still in the current configuration, but expressed in terms of the Lagrangian coordinate or the referential coordinate. Okay? So I'll just mention that it is not the velocity of the particle in the referential configuration, in the reference configuration. Okay, please be very clear about this. Anyway, so I'm going to stop the class here, but I'll take your questions. So somebody is saying, can you explain intuitively how mathematically Lagrangian expression relates with tracking a particle, material description? Yeah, of course, because you see this Lagrangian description, for example, this velocity x comma t. So in this description, you have to tell x, and then at different time t, it gives you velocity. But then you know that to every x, there is a unique particle p. To every x, there is a unique particle p. And that's why Lagrangian description is equivalent to tracking the particle. Whereas in the Eulerian description, this v hat of y comma t. So when you fix your y and just change time, so that means in the spatial, in the three-dimensional space, you are looking at a particular point in the space and at different times. So at that point in the space, you will have different particles coming to it at different times. And the velocity is then of different particles at different times. It's not of the same particle. Therefore, you are not tracking a unique particle in this Eulerian description. Whereas in the Lagrangian description, when you fix x, that is equivalent to fixing particle. When you fix y, it is not equivalent to fixing particle. Isn't it? Because you know, when you take the inverse, at different time, inverse of y will give you different particles. So that's why fixing y is not equivalent to fixing particle. Fixing y means you are fixing a point in the space, and at different times you will have different particles passing through it. Okay.
Sir,
Yeah.
in reference configuration topic, you drew three figures where we were mapping the particles in the reference configuration and in the current configuration from the same body.
Yes.
So, sir, my question is that how can the same body be used for mapping two different regions? Because if regions have changed, so will be their respective bodies will be changing. So why
No. So I
single
think
body is
you are
used
trying
for map?
to. Yeah. Yeah. Okay. That's a good question. See, it's a matter of definition. By body, we just meant collection of particles. By body, we are just meaning collection of particles. It is not the physical body. It's a mathematical body, which is simply the collection of particles. So why will that change? It is a collection of particles. No, it is not going to change.
Sir,
The
suppose
particles are
we
all the.
suppose sir we are heating a body.
Yes.
So the particles positions at t equal to 0 will be something else, and at t is equal to t time the particle positions will be something else. So for
Yes.
mapping, these two different bodies should be used for mapping different configurations of reference and the current region.
Hmm.
So the bodies
See,
have changed at different times, no, sir? If
correct.
regions have
But
changed, then
that
bodies
body,
have also changed.
I know. So see, that is the problem here. The body that I am mentioning in the class, it's not the physical body. It is a mathematical abstraction of the actual body. It just means collection of particles. And when I say collection of particles, it is not the collection of position of particles. It is just collection of particles. Let us say when you number particles 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, then it is collection of those numbers. Okay, it
Okay.
is not the collection of positions of those particles. It is just collection of numbers. It's just a mathematical thing. So that will not change. Even if you hit it, even if you break the body, it is the same particles, even after it is broken, that you are looking at. So the collection of those particles is still the same.
Okay.
It is the same particles that you are looking at. Yeah, good question.
Okay, sir.
Hello, sir.
Yeah,
Can you hear me, sir?
yeah, tell me.
Sir, I think Meenal asked one question. She asked, we have a reference configuration and then we have the inverse of the reference configuration of a body. So does inverse of reference
Yeah.
configuration depends upon time or not? She asked this.
Who asked?
Meenal.
Meenal. Oh,
Yes,
okay.
sir.
In the chat box. Okay.
Yes, sir. Yes, sir.
Reference inverse function should not depend on time, right? Of course, it will not. Because reference configuration, when it does not depend on time and the body does not depend on time, then the inverse will also not depend on time. Let me show you that picture here. So that's the first picture that we did today, right? So you are referring to this thing, no? So you can see that the reference configuration is independent of time, the body is independent of time. So then the inverse or the direct map or inverse map, they will all be independent of time. If I have to introduce time here, so let me then introduce it. So this thing here, this also goes away, this also goes away, this also goes away, and then I put time. Comma t, this is comma t, this is comma t, and that's also comma t. Okay, but the reference and the body thing, there is no time there. Okay.
Okay, sir.
Sir, I think this question
Hmm.
came
Very
because
good.
in the velocity term, like when we were writing the
Yeah.
velocity, we wrote x reference inverse uh, x comma t. Uh, so at the end, like when we were defining the velocity at that time, I think you wrote uh, xi inverse ref.
Okay. Yes, you're right. It will not be the case because here the inverse is being done for the particle, no? So so thank you. So this was my mistake. It is
Yes, sir.
just
Time should
this.
not be there.
Thank. Yeah.
So one just small basic question from last lecture only, like that three body we have shown. Basically, one collection of particle is the main body, and then we have reference configuration and our current configuration, and finally we relate reference to the current. Then the definition of
Correct.
as a abstract body, which is like collection of particles which we have thought of in that body, that middle body. So that is like nowhere in the picture now. So whether that abstract definition or whether
Yes.
it is going to still hold good and help us in future, because we have directly now connected from reference to the current.
Correct.
So the
Yeah, that is true.
that definition of body as collection of particles, whether still that will hold, because I think we will not be again going into the that body without having boundaries and all. Now we have gone in more like realistic frame, where from reference to the current we are connecting. So the middle step will
That is
have any
correct. And
significance?
yeah, that's a very good question. And if you look at the book, no, it is they have also talked about this point. They say that somebody is making noise. I don't know why these guys are making noise. Anyway, so you'll see that in the book it says there are formulations where the reference configuration also changes. Okay, so in
Okay,
such
sir.
formulations, always a good idea to have this picture of the body so that we know that it has to finally correspond to particles.
Understood, sir.
Yeah.
Yeah, in such cases it will be required that from body to reference. I mean current configuration also that relation.
Yes. Yes.
Okay, sir. Understood. Thank you, sir.
Sir, can we say that body is the region occupied by the region occupied at T equal to 0? Because after we heat,
No, it is not.
the particles will
Suno, Sanjay bro.
shuffle up, sir.
Wait, wait, wait. Please listen to me. Listen to me. Body is not the region occupied at T equal to 0. आज ये देखो, तुम्हें लिटरली सुनना है मुझे, तुमने अपने दिमाग में कुछ बना लिया है और वही तुम सोच रहे हो. Just listen to me. Body, as we are discussing in this class, a mathematical body is just a collection of particles. And when I say particles, it is not I don't refer to the location of the particle, just particles. Let us say if you could number the particles 1, 2, 3, 4, 5, 6, it is just collection of those numbers. So इस बॉडी से हमें पता नहीं चल रहा है कि एक्चुअल फिजिकल बॉडी का क्या शेप है, या वो t इक्वल टू 0 पर कहाँ था या t इक्वल टू 5 सेकेंड पे कहाँ था, हमें ये बिल्कुल पता नहीं चलेगा. ये जो डिस्क्रिप्शन ऑफ बॉडी हम लोग क्लास में बात, आई होप यू कैन अंडरस्टैंड हिंदी. कैन यू?
Sir, only 18 seconds are left.
Yes, sir.
Yeah. So what I mean to say is that it is just the collection of mean the position of the particle. It is just collection of numbers. तो उससे कहाँ से पता चलेगा कि बॉडी का क्या शेप है? वो सब नहीं पता चलेगा. अब ये सोच के, so that's the body, and the reference configuration is actually the body है in some convenient configuration. Or current configuration is of course the physical body in the current configuration. वो है.
ठीक है.
Body
ठीक है.
is not a physical body. It's just a mathematical collection of particles.
ठीक है सर. ठीक है.
हाँ.
Okay, sir.
It's a bit confusing when I write it with body, but this is how people have been discussing, and I'm also saying it's a mathematical body, so it should be clear that it's a mathematical body and not a physical body.
Okay, sir.